Hello and welcome to Lecture 3B Integral Control. Today we'll be learning about what is integral control, how to use it, and the goods and bads with integral control. This is a continuation from the last lecture where we looked at proportional control. Okay, so what is integral control? Well, it looks like this: Ki multiplied by the integral of error in time. So what is this? So Ki is the integral component, or parameter, and this is the value v tune, so a numeric value that we are tuning. Important to say numeric because it's just a value, like a decimal. Could be 2, could be 5, 0.1. And then this part over here, which I'll draw in green, this integral, well, that is summing the error over time. Summing the error over time. So if I draw you a graph here, so that's a graph, and that line, horizontal line, is our set point. If you have this blue line, which is our steady state, so our summing the error, so remember all of these differences between the blue line and the green line being the set point, is an error. So for those who are not too familiar with integration is finding the area under a curve. So we are actually looking for the area under this curve, and this makes our error. So the way we do this, so let me just erase this graph and draw a better graph. Orange is nice. So that's our set point of, so whatever the set point is. And then we have our curve. So what we do in integral control is we're constantly sampling, because we're a computer, we are sampling. And then we see what is the error over here, so that's the error 1. What's the error over here? That's the error 2. Over here, and then all the way down here to error of time n. And this could be seconds, so this could be time, that's 1, 2, 3, 4, 5, n, whatever, that could be time. And so what summing the error over time means is we take these values and we add them together. Perhaps I could improve with my spelling, but we are adding E1, E2, E3, E4, and all the way to En. We are adding the errors here. And what that does is it sums the error over time. And this is very useful for steady state typically. So let's clear everything. So useful for steady state. And essentially what it does is it scales up the sum of the error, which essentially means it's taking a history, it's tracking the error over time. So it's tracking error, the error over time. And this is very useful for very small, tiny steady state problems where, for example, the steady state might be, say, a few degrees away from the set point. So good for small steady state errors. So if I draw another graph, so you could see what I'm talking about, clear all that. So imagine you have this graph here, and that's our set point. And now we've passed transient response, and now we're at a steady state. And this happens to be our steady state. This really, really flat oscillation. Well, integral is actually really good at dealing with steady state errors. So this error here, because we are simply summing up the errors, if you sum up these errors over a long period of time, of course the error is increasing. So by scaling that error, we cause our system to compensate more, and that can flatten the curve. That can flatten this line here, so perhaps you would get this instead. So sum error, then we multiply scale the error, and then by scaling the error by a good amount, the system will correct itself. So controller will correct it, will correct these small errors. So remember, very good for small errors. But one major problem with integral being, what happens if there's a huge overshoot? I can draw it in blue. But if you have this random spike here, well, the problem with integral is it's actually summing all of this the area of this massive peak. So massive overshoot. So one of the issues with integral being, if you have massive overshoots or a massive spike of noise, well, what can happen is integral can become too aggressive. So integral may be too aggressive. Integral may be too aggressive. So you really need to be careful with integral control, because remember, we are summing all of these points here. We are summing all of the errors in time. So if you have some huge overshoot means a massive compensation, which means, of course, massive error. And massive error means there's a large compensation or overcompensation or undercompensation of the system. So overcompensation or undercompensation. Remember, that's because the system thinks the error, or has scaled the error larger, so the controller thinks the error is larger than it actually is. So if you have this overshoot here, well, in reality, that could be a small overshoot, but your integral controller, if you've tuned Ki to become large, will think it's a huge error, and because you have a huge error, the system is trying to compensate for a huge error, and that's very bad. It can cause overcompensation or undercompensation. And remember, when you have overcompensation, what happens is you go up, but then the controller is too aggressive, so the controller undercompensates, and because the controller undercompensates, it's an aggressive controller, so it goes all the way up, so that leads to oscillations. So typically, one problem you find with integral control, if your integral control is too high, it leads to overcompensation, and overcompensation leads to undercompensation and oscillations, or vice versa. So in green, if Ki is too large, then if there is a massive, in the event that there is a massive overshoot, integral control could be too aggressive. So if you have a huge overshoot, you have a massive error. Massive error means overcompensation or undercompensation, and any of these two problems here leads to oscillations, and that means your system is very unstable. So that's unstable. So don't make Ki too large, but at the same time, if I just delete everything, if you make integral control too small, so if Ki is too small, then what actually happens is, because remember, you're summing the error over time. So imagine this is your oscillations. Well, it's a lot slower to respond to the system. So like the oscillations will decrease eventually, but it's a lot slower. You can make those oscillations disappear quicker by just increasing Ki, by making Ki a little bit more aggressive. But if Ki is too small, well, then your system just takes ages to correct itself. So the steady state error takes too long to correct. So steady state error takes too long to correct. So how to actually use the integral controller. So firstly, make ki, or the integral parameter, large enough to remove any small steady state error or offset. Errors or offset. Offsets is like a constant value away from the set point. But then don't make ki too large, because then you will become unstable if there's any overshoots. So, but do not make it too large. Or the system becomes unstable. The system and controller become unstable. That's a key term. It becomes unstable if ki is too large. So what's the goods about ki? So ki removes small steady state errors. Integral also keeps track over history, so it keeps track over time. So that means our controller can adapt over previous events. But then the bads, so the bads being unstable system if ki is too large. Summary. We learnt what integral control is and how to use it. We then learnt the goods and the bads with integral control. Okay, now for my favourite part of the lecture, which is the end. Thank you. Our next lecture will be Lecture 3C, which is differential control. See you next time. Thank you.